Good morning, everyone. So, hopefully, everyone is here. So, if you are here, please leave a message in the chat. Today, our discussion will be mostly on normal subgroups. So, I think we can start with the session today. Uh, Please leave a message in the chat if you are online. So hopefully you can start with the session today. So last lecture we saw why do we need normal subgroups and what is the motivation behind it, and we defined what is a coset, right? I think we stopped there and we started finding cosets for different groups and subgroups. So today I'll give you the classical definition of a coset. How do we define coset? The classical way, and then we will move into defining normal subgroups. There are many equivalent definitions. We are not going to prove they are equivalent, but we are going to state it in general. Okay. So today we'll be defining cosets in the classical way, defined, and then we will move into defining what is a normal subgroup. So last class, if you remember, we started giving the motivation for normal subgroups by saying that we are going to we are going to split the set so that given any homomorphism, it becomes a 1-1 map. That is what our motivation to define a normal subgroup or a coset. Now, whenever in general in pure mathematics, whenever we need a set to be partitioned into different sets, the usual trick is to define an equivalence relation on it. Okay, so this is the usual trick. Whenever we have a non-empty set, if we want to partition the set into different pieces, so what we do is we try to define an equivalence relation on it. So equivalence relation, what it does is it partitions the set into disjoint sets so that the union becomes the entire set again. Now, what we are going to do is we are going to define a relation and try to prove it is an equivalence relation, and hence what we will show is this equivalence relation will give us some equivalence classes. So these equivalence classes, what it does is it splits the set into different disjoint sets whose union is the entire set. So we'll define what is the equivalence relation. So now let G be a group, H subgroup of G. Now let on the set G we are going to define an equivalence relation. So let A comma B belongs to G. We say A and B are related. We say A and B are related if and only if A belongs to G. Take A. And since B belongs to G and G is a group, we will have something called B inverse. So this A B inverse must belong to this subgroup H. So this might be a bit tricky to understand, but let us see. So what we are doing is on the group G, now we are considering it as a set, and we consider a subgroup H of G. So given any A and B in G, we say that A and B are related only when A B inverse belongs to H. So in the abstract sense, you will try to prove it is equivalence relation. So you will be even more clearer when we try to prove for different groups. Okay. Now, so to prove something relation is an equivalence relation, uh, what we will do is we will prove three axioms, three properties. So it is reflexive, symmetric, and transitive. So reflexive, it says is what we need to prove is A is related to A. To prove that is what we need to show is that is to prove A inverse belongs to H here. Right? Now take A inverse. Now clearly we know this, since it is in the group G, A inverse is equal to identity. And since H is a subgroup, this belongs to H. And hence implies A is related to A. Fine. So reflexiveness is true in this for this relation. Next we need to prove symmetric. Assume A related to B, and we need to show that B is related to A. Now since A is related to B, AB inverse belongs to H. Now, so since H is a subgroup, its inverse is going to be in H. And if you are clear with the basic properties of a group, and this would be nothing but B A inverse, which belongs to H, because this will be nothing but B inverse the whole inverse into A inverse, which is B A inverse, and this will imply B related to A. So whenever for this relation symmetric property is true, and then transitivity is true, obviously we will try to show that now. So this is just for you to warm up. So this is a very simple exercise which we can try. So assume that A related to B and B related to C. So this will imply AB inverse belongs to H and BC inverse belongs to H. We need to prove A is related to C. So you need to show AC inverse belongs to H. To show that A related to C, that is AC inverse belongs to H. So AC inverse, you can write it as A E C inverse. Just I am operating the identity in between. You can write this as A B inverse B C inverse. The reason why we do this is we know that AB inverse belongs to H and BC inverse belongs to H, and we are trying to use it. So by associativity, this will be AB inverse, BC inverse. Then since this belongs to H and this belongs to H, and since H is a subgroup, this belongs to H. Now we have proved that this relation on any group and given any subgroup of it is an equivalence relation. So given an equivalence relation, what we try to do is we try to split the equivalence classes and then try to proceed. So what we do is now we try to do an example where we define such an equivalence relation and then we will proceed. Okay. So the obvious example what we do is consider z comma plus. So let this be g and we take h to be say 3z. That is multiples of 3. So we define an equivalence relation on z. So let a comma b belongs to z. So how did we define it? A b inverse must belong to h. Here what it means is a, since this is addition, inverse of b is going to be minus of b. A minus b must belong to, what is our h? 3z. Fine. That is a minus b is a multiple of 3. Okay. Now we will try to check how the equivalence classes behave here. So our ultimate aim is a and b will be related whenever a minus b is a multiple of 3, integer multiple of 3. As simple as that. So please leave your clarifications here. I have been defining quite a few things from the start today. So please be free. Please feel free to ask your clarifications in the chat. Now, so we will try to check what will be the equivalence classes. So A is related to B if and only if A minus B belong to 3Z. Fine. Now, first what we will do is we try to collect say all elements which are related to a particular element, and then we will try to build up from it. Okay. So first we will collect all elements which are related to 0. So we denote the equivalence class by this notation. So can you guess what are all the elements will be related to 0? If you have any, if you have your answers, please mention it in the chat. So can you guess what will be the elements which are related to 0? Okay, good. There is an answer from Mahesh. It is going to be 3z. Let us check why. So if let us check whether 1 is related. 0 minus 1 is going to be minus 1. So which is not in 3z. So 1 is not related. Same way through 2 is not related. 3 will be related because 0 minus 3 is minus 3 which belongs to 3z. So similarly, if you check, what happens is 0, 3, 6, etc. and minus 3, minus 6, etc. So these are all the elements which are related to 0. Fine. Now, so we have collected all the elements which are related to 0 here. Now let us check what are all the elements related to 1. Now, an element will be related to 1, an element B will be related to 1 when, because 1 is not here, we can check this. Okay, maybe we will come to that later. So we are checking what are all the elements related to 1. So what are all the elements related to 1? By reflexivity, 1 will be in this set because 1 is related to 1. So there is an answer from Mahesh. 1 plus 3 is there. Good guess, but we haven't defined what is 1 plus 3 z yet. So we are on the process of defining that. So we will use that notation a bit later. Okay. So yes, Pranati, it is Your observation is perfectly correct, but we will define what is 1 plus 3z after this. Okay. So we haven't given the classical definition of coset yet. Okay. Now, so 1 is related to it. Then the next element which is related to it is 4 here, because 1 minus 4 is minus 3. In the same way here, it is going to be minus 2, because 1 minus 2 is going to be 3. 1 minus 2 is going to be 3, which belongs to 3z, and hence minus 2 belongs to this set. So 7, etc. This way it is going to be minus 5, etc. Okay. Now, next, let us collect all the elements related to 2. Now you would have easily guessed what will be the elements related to 2. So the elements related to will be 2, 5, 8, etc. And this way it is going to be minus 1, minus 4, etc. Right? Now what I claim is, we did not check the equivalence classes of the other elements. We need not check the equivalence classes of the other elements. The reason is, the next obvious guess is what will be the equivalence class of 3, but 3 is here. So the equivalence class of 3 is going to be the same as equivalence class of 0. The equivalence class of 2 is going to be the same as equivalence class of 5. The equivalence class of 1 is going to be the same as equivalence class of 4. Because we are collecting all elements related to 1. Okay. There is a question from Pranati. Why? Okay, good. So let us check what is equivalence class of 3. And then we will try to generalize the abstract way why it is true. So we will collect all the equivalence classes of 3. So it is going to be first 3. And then it is going to be 0 is going to be related to 3. So 0. Then oh, fine. Okay. So you are saying that it is true. Okay, fine. Okay. Now, so this is going to be, so what happens is, as we stated earlier, an equivalence relation partitions the set into disjoint sets known as the equivalence classes. So if you see carefully, these 3 sets cover the set on which we define the equivalence class. See, 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. And this way, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, etc. So if you union these 3 sets, we are going to get the entire set. Fine. Now, there will be no other equivalence classes other than these 3. But please be careful, the notation might vary. I need not represent this as 0. I can even represent it as equivalence class of 3. Or I can even represent it as equivalence class of 999. Whatever it may be. Any multiple of 3. Fine. There might be different notations representing this equivalence class. Yet the set is going to be the same. So for 3z, with respect to z, there will be 3 equivalence classes. So with respect to this relation, not just this, in general, with respect to this relation, the equivalence classes we get are called the cosets of H. So given a group and a subgroup, we define an equivalence relation. A and B are related whenever AB inverse belongs to H. And hence, the equivalence classes we get from that relation is going to be called the cosets of H. Okay, left cosets of H. What are it? Fine. They are going to be called the cosets of H. We will see what is left coset and right coset later. Fine. Now, so here the cosets of H are nothing but these 3 sets. As simple as that. Only these 3 sets form the cosets of H. Right? Some of them might be left and some of them may be right. We will see that later. So if you look at it carefully, as some of you mentioned in the chat, this is nothing but 0 plus 3z. This is nothing but 1 plus 3z. This is nothing but 2 plus 3z. So this is just a notation. So we said, right, coset notation is AH, where this the operation between operation in the loop. Here addition is the operation. We denote it by 0 plus 3z, 1 plus 3z and 2 plus 3z. It's not necessary that we are going to represent it only this way. You can even represent it, as I said here, you can even represent it as 3 plus 3z, 6 plus 3z, etc. Fine. So if you have any clarifications, please leave it in the chat. We will proceed on defining the normal subgroup now. Okay. Okay. Now, as we said earlier, if G is a group, so G1, and we define any homomorphism, we are trying to partition the set into different disjoint sets, so that what happens is the map in which we do can be made into a 1-1 map. We are trying to make a 1-1 map here. So what we do is, now we have defined how to partition this set into distinct disjoint sets. So what we are going to do is consider a subgroup, say H. Fine. Now this is going to be the coset with respect to the identity element. Fine. Now collect all possible cosets. Collect all possible cosets. So what it does is, clearly by our definition of cosets, what it does is it splits the set into disjoint sets whose union is the entire set. So these are all the equivalence classes with respect to the relation which we defined. So each one is a distinct equivalence class of an element here. So these are all the cosets with respect to a particular subgroup. We will define what that subgroup to be later. Now these are all subgroups. Sorry, these are all cosets related to this subgroup with respect to this subgroup, and we are going to use this to split the set into different equivalence classes. Now, before moving on to that, I said we are going to, given a homomorphism, we are going to try to make it as a 1-1 map. But to define that, we need this to be a group first. Fine. So now what we are going to do is we are going to consider each set as a single element. This set will be a single element. So what we do is, say, I will define it. Let H is equal to collection of all possible cosets. Okay. So Pranati, in previous example, 3H is your G. Okay. No, 3H will not become G. Your H is 3Z. So 3 plus 3Z is going to be again the same. So there are, if we consider the previous example, if this is Z, it is 3Z, 1 plus 3Z, 2 plus 3Z. There are only 3 cosets. There are only 3 cosets. We have split the set into 3. Okay. Hopefully it is clear now. Now what we are trying to do is, we are collecting all possible cosets. Okay. So we are collecting all possible cosets. We will denote it by EH, some A1H, A2H, etc. So for now, assume it to be a left coset. Okay. So we are collecting all possible cosets. So these are all, each one is a coset. So our ultimate aim is to define a homomorphism by considering each one of these as elements. But the problem is this, to say this will be a homomorphism to some other group, this must be a group. This X must be a group. So there must be a binary operation defined on it, and with respect to that binary operation, we need to show it as it forms a group. Fine. Now, so we are going to define a binary operation in such a way that this becomes a group. So let us try to define the binary operation. So there, take two cosets. These are all the elements of this set. Please be mindful of the fact that each one is a set here. This is a collection of sets. Okay. Now, how we are going to define is, take two elements, say A1H, A2H. We are going to define an operation between these two elements. Now, an obvious operation would be A1, A2, H. Fine. An obvious operation, because we know there is an operation between A1 and A2 because they are elements in G. So find the left coset of A1, A2. But the problem is, this operation need not be well defined. That is, let us look at it carefully. We will try to arrive at it from here. So A1H equal to H, A2H. Let me write it as A1H, A2H. Fine. Now, we are trying to write this as A1, A2H. So, it means that we are trying to switch the position of A2H, HA2 as A2H. Fine. But if you are trying to switch the position of HA2, it is not equal to A2H always. So, left coset and right coset need not be equal in general. In general, it need not be equal. Since we have arrived through examples only having having abelian groups, so we haven't arrived at such an example. We will try to look at such an example when we move into symmetric groups. Fine. Now, in general, the set AH is equal to AH such that H belongs to H, and the set HA equal to HA such that H belongs to H need not be equal in general. In general, it need not be equal. It might be equal at times. It might not be equal at times. So in general, this need not be equal. So to switch the places of HA to H and A2, if suppose this is equal to A to H, what we can do is we will try to switch the places A1, A2, HH, and this is going to be nothing but simply H, because this is a subgroup. You are multiplying two elements of the subgroup and it is going to be the same. You are taking two elements, okay, fine. So we will say what this is. HH is set of all H1, H2 where H1, H2 belongs to H. Sorry. So HH is set of all H1, H2 such that H1, H2 belongs to H. Since this is a subgroup, this is going to be again in H. So this is a subset of H, and H is obviously a subset of this, and hence HH equal to H. So this is going to be H. So everything here happens, the operation is properly defined only when you can switch places of H and A2. That is, for any B or any A in the group, AH must be equal to HA. Only then we can define this to be the operation, binary operation. So what we are trying to do is we are going to restrict the property on the subgroup where the property on the subgroup must be like every left coset of that subgroup must be equal to its right coset. So we are restricting the properties which we do only to those subgroups which have this property with them. Okay. So if we do this, then we will be able to define a binary operation on this collection of sets. And hence, after defining the binary operation, it will be trivial to prove it is a group. So what we do is, to define this, we are going to name such a subgroup with a special name. That is what we call as normal subgroups. So let H be a subgroup of G if for every A in G, AH equal to HA, then H is called the normal subgroup of G. That is, given any A in G, left coset must be equal to right coset. So then the subgroup will be called the normal subgroup of G. There are many equivalent definitions for this. There are many equivalent definitions for this. So let us try to look at few examples where the subgroup we take is a normal subgroup. Fine. So you will try to, I will give you the example, I will give you the subgroup. Please try to calculate the left cosets, all the left cosets and all the right cosets, and check whether they are the same. Okay. So let me give the obvious example first. Say Z9 under addition modulo 9. Fine. So Z9 under addition modulo 9 forms a group. Now let me give the subgroup H to be, say let us take subgroup generated by 0, 3, 6. Let us consider this subgroup. Fine. Now what is our claim is to prove that, to try to prove that this is a normal subgroup of Z9. Fine. Now, so first what we do is, this will have 0, 1, 2, 3, etc. up to 8. So the first aim is to find all the left cosets. So what will be the left cosets? 0 plus H, 1 plus H. So the operation is addition modulo 9. 2 addition modulo 9 H, 3 addition modulo 9 H, etc. till 8 addition modulo 9 H. So try to calculate all these, please. We will have few observation and we'll try to state it down as a result. We'll try to calculate this. Please calculate this, and we will try to have some observations from here, and then we will state that down as a result. Okay. So 0 plus 9H is going to be 0, 3, 6. 1 plus H is going to be 1, 4, 7. 2 plus 9H is going to be 2, 5, 8. 3 plus 9H, 3 addition modulo 9H is going to be 3. 3 plus 3 is 6. 3 plus 6, 9, which is 0. Okay. So it goes on. Fine. Now, please check whether the corresponding right cosets, that is H plus addition modulo 9, 1 is the same as this. If you are more watchful, you will give the answer now. If you are more watchful with what I say and what operation we define, you can give the answer very easily. Okay, Mahesh says that this will be a normal subgroup. That is, every left coset and right coset will be the same. Can you give us the reason, Mahesh? Okay. So Pranati says A plus H is equal to H plus A uh, for every A in Z9. And yes, it is true. Pranati. Karpadam, Z9 is abelian, so every left coset is equal to its right coset. Good. So Mahesh says that every subgroup of an abelian group is normal. Okay. So we are on the verge of saying that. We haven't said that yet, Mahesh. So since it is abelian, we are trying to guess here that every subgroup will be normal. We are just guessing till now. So if we look at the set definition properly, we will go on to the definition of coset. AH. How did we define AH to be? AH such that H belongs to H. Fine. Now, if suppose the group is abelian, H is also an element of the group G, right? Because it is in the subset, it is going to be in the whole set. So AH will be defined as AH such that H is in H. Since if suppose if you assume the group to be abelian, what happens is this is going to be equal to HA, where H belongs to H, and this is nothing but the right coset. So if you have a left coset, is defined as AH where H belongs to H. If suppose if G is abelian, given any A, AH will be equal to HA, and hence this is to nothing but the right coset. So our left coset must be equal to the right coset. So H is normal in G. So whenever G is abelian, if we consider any subgroup of it, it is going to be a normal subgroup. Fine. So it is not necessary to check these things. So that is what my aim is to say. So in general, if we feel that if we have proven that the group is abelian, whatever subgroup we take, it is going to be a normal subgroup. Okay. Now, so we will state our observations here. We will define few things and we will state our observations here regarding cosets and also regarding normal subgroups. Right? The first observation is EH is equal to H. Okay. Now the second observation will be easy for you to prove. Yet we will try. AH equal to H if and only if A belongs to H. This will be a statement which will be used often in our proof techniques. Very often it is going to be used. More used, but it is very trivial to prove. Fine. So maybe you can try to prove it on your own. It is very simple. Just use this fact and use the definition of cosets. So how did we define the cosets? We defined it using equivalence relation. We said that A and B are related whenever AB inverse belongs to H. So we are going to prove this coset is equal to this coset and try to prove it that way using this definition. Fine. So AH will be equal to the subgroup itself, the left coset or the right coset, any for that matter, anything. HA or AH will be equal to H if and only if the element we consider is going to be in the subgroup. Right? Now, the third property is if G is abelian, then every subgroup of G is normal in G. So if the group is abelian, then every subgroup of G is normal in G. Now the next observation is, I stated this observation in the last class. Let me recall it again. This is regarding the coset. If order of H is equal to n, then the number of elements in AH will be equal to n. Means in AH is n. If H is infinite, the number of elements in H is going to be AH is going to be infinite. That is, the subgroup and the coset will have the same number of elements. Okay, so this is these are all the observations which we have done so far. These three are regarding the cosets, and this is a specific property about the normal subgroup. So okay, so there is a question from Pranati. Sir, how to check any given subgroup is normal or not easily if group is not abelian? Okay, so this is what we are actually proceeding on. In general, proving a group to be normal is not so simple or trivial. It takes time. If we try to find all the cosets, if suppose the group is infinite, if we take all the cosets, if we try to take all the cosets, it takes lifetime. Fine. If there is no general form, so it is actually a tedious process in general. So what we are trying to do is we are gradually proceeding so that the process of checking a subgroup to be normal will be simplified using group homomorphisms. That is what we are arriving at. So we are slowly building up so that we can hereafter check a subgroup to be normal using group homomorphism. So we will build up, and I will, when we come to that stage, I will clearly let you know. Okay. So as I said earlier, there are few equivalent definitions for normal subgroups. So after seeing that, we will proceed on to something which is our ultimate goal in normal subgroups. Okay. So these are all equivalent statements. I will just state the definitions. I'm not going to prove they are equivalent or anything. You can try to verify it. So let H be a subgroup of G. H is a normal subgroup of G. So maybe I will write it this way. H is a normal subgroup of G. Second statement, for every A in G. Okay, so that is what we define. So every G in G, G H G inverse equal to H. This is one equivalent statement. every G in G, GH, G inverse belongs to H. This is another equivalent statement. I think these three are more than enough, I guess. So by definition, by a normal subgroup, it is nothing but if for every G in G, GH is equal to HG. So these are actually different versions of the same definition, yet it is not trivial to prove these. You need some more analyzing capacity of properties of groups so that you can prove these statements to be uh, equivalent. So these are all different definitions of normal subgroups, and we will, depending upon the situation, we will use whichever is possible. Fine. Now, so these are all the definitions for on the prerequisites for defining what we call as the first fundamental theorem. We are going to state the first fundamental theorem of homomorphism. So we are going to proceed towards that. So for that, we need these prerequisites. Right. Now, as we defined earlier, we call phi from G1 to G2 to be a homomorphism when for every x comma y in G1, phi of x y is phi of x comma phi of x into phi of y. Okay. Now, we saw this earlier. So as I said, I repeat again, our aim is to try to convert this mapping so that this becomes a homomorphism. Okay, so sorry for going into this. Before this, we need to define something. Quotient group. Quotient group. We'll define what is a quotient group or a factor group. There are different ways of saying this: quotient group or factor group. So let H be a normal subgroup of G. Then quotient group of H in G is defined to be G. Some of them pronounce it as G mod H, and some of them pronounce it as G by H. So whatever it may be, this is nothing but a collection of all left cosets. As simple as that. So this will form a group with respect to the operation for every A comma comma BH in G by H. We define the operation to be AH into BH equal to ABH. That is, take a left coset and take another left coset. The operation is nothing but we try to operate the elements in the group and then find its left coset. And we saw that this is valid only when the subgroup is normal. Only when the subgroup is normal. And you can check that this forms a group. So the identity element is going to be EH, and the inverse of AH is going to be A inverse H. So G mod H is called the quotient group of H in G. Okay, I don't think it is called as quotient group of H in G. Quotient group of G. Enough. I think depending upon the subgroup, we will use that. So G by H forms a group with respect to this operation where the identity element is EH and the inverse of AH is A inverse H. Right? Now we will go into defining what is kernel. What is a homomorphism? Kernel of a homomorphism. So as I said, phi is a homomorphism from G1 to G2. Phi of x y is equal to phi of x phi of y. Now G1, G2, there is a mapping defined to us. So clearly there will be an identity element here and identity element here. Let me call it as E1 and E2. By properties of homomorphism, E1 will be mapped to E2 under this mapping phi. But it is not necessary that only identity will be mapped to identity. There might be many other elements which might be mapped to the identity element of this group. Say some other element G, some other element H, some other element W. So there might be many different elements which might be mapped to the identity element of E2. Now what we are trying to do is we are collecting all such elements and put it inside a set which we call it as kernel of this homomorphism. So we call this set as the kernel of the homomorphism. So we define kernel phi to be collect all elements in the domain, whose image is the identity. We are collecting all elements in the domain whose image is the identity. So we will try to find for few examples, few homomorphism, what is kernel, what will be the kernel, and we define few properties of kernel. Okay, so kernel is collecting all elements in the domain which are mapped to the identity element of the codomain. Okay, so let me give you few homomorphisms and please try to collect what will be kernel of phi. Okay, so let me give a homomorphism from Z phi to Z phi. Okay, where the mapping is defined to be not Z5, maybe I will use Z6. So where the mapping is phi of x is equal to x plus, or maybe I can denote it as 2x, but still, so phi of x is x plus x. So please try to find what will be the kernel of this homomorphism. Please calculate it now. First check whether this is a homomorphism. Okay, maybe I will give you that relaxation. This will be a homomorphism. Try to check whether this is a what will be the kernel of this. Maybe you can leave out your answers in the chat. So for this homomorphism, what will be kernel? So kernel of phi is set of all x in z sets such that phi of x equal to 0, because 0 is the identity element in z sets. Fine. So maybe let us check what happens to each element and then we will find the kernel. Okay, Pranati, yes, it is true. It is 0 and 3. Fine, maybe let us verify it. Right? So what is phi of 1? It is 1 plus 1, 2. Phi of 0 is 0. 0 plus 0, 0. So this is going to be, this will have 0 in it. because it is mapped to 0. Phi of 1 is 2. Phi of 2 is 2 plus 2, 4. Phi of 3 is 3 plus 3, 6. But with respect to mod 6 in Z6, since we are working in Z6, we are going to use mod 6. So 3 plus 3 is 6. So it is going to be 0. So we are collecting this. We are collecting the elements in the domain. Please be careful with that. So by kernel, we are saying that we are collecting elements in the domain whose image is 0. Okay, fine. Now, phi of 4 is 4 plus 4, 8. With respect to mod 2, mod 6, it is going to be 2. And phi of 5 is 5 plus 5, 10. With respect to mod 6, it is going to be 4. So if you check here carefully, the elements are mapped to 0 or 0 and 3. So our kernel is 0 comma 3. Fine. Okay. Let me do another homomorphism from one set to another set. Please try to check what will be the kernel. Fine. So maybe we'll just change for a different n. We might define it for between, there might be a question, why do I define it between the same groups? We might define it between different groups, but for a beginner, it is better we deal with the same groups on both the sides. Okay. Z9. We define the operation to be okay. Maybe we will define the same operation. We'll define the same mapping. Try to check what will be the kernel of this mapping. Try to check what will be the kernel of this mapping. Okay, so there is a answer from Pranati. It is only 0. Okay, yes. Okay, Karpadam, good. It is only 0. So maybe we will verify it. So phi of 0 is 0, 0. Phi of 1 is going to be 2. Phi of 2 is 4. Phi of 3 is 6. Phi of 4 is 8. Phi of 5 is 1. It was 5 plus 5, 10. Mod 9, 0. Phi of 6 is 3. Phi of 7, 5. And phi of 8, 67. Okay. So the kernel here is only the singleton 0. So here till now in the two mappings we defined, we have few observations. 1. Kernel is always non-empty because 0 will be, the identity element will be mapped to the identity element. And 2, in these two examples, what we saw is, how could I say that? So in these two examples, what we saw is the kernel happens to be a subgroup of the domain. Here, in these two examples, what happened was the kernel happened to be the subgroup of the domain. Because in Z6, we saw the kernel to be 0 and 3. In this mapping, we saw the kernel to be just 0. So both are subgroups of their respective groups. Fine. So in general, we might have an observation that this might be a subgroup. Okay. So we will. So this will be a good exercise to try. So kernel of a homomorphism is always a subgroup. First observation. The second observation is even more beautiful. Let us try to prove it in general. Okay, maybe I think I should give one more example uh, before going into defining the before going into stating the fundamental theorem. So can you spare me some 10 more minutes? So I think it is an hour nearly now. So just 10 more minutes. Let us wind up. Okay. So just 10 more minutes. So I will give you one more example, and then we will quickly state down the observation which we did today. So let us define phi from z to z by phi of okay, not z. Maybe so. This will be an example which will be clarifying your doubts. Maybe I will define the mapping from z to z6. Define phi of x is equal to x mod 6. So this is not the proper notation. Okay. Pranati, there is an observation from Pranati. Kernel of phi is phi of m is if m is even in zm. Okay. 0 if odd. Pranati, I think it is too quick to have this observation. It is not true in general. Because that is by phi of m, I think you are trying to say the subgroup generated by uh, I think you are trying to say something related to subgroup generated by it. So I think it is too quick to get into that observation. There are different homomorphisms where this fails. So maybe we will look into that soon. Fine. Now, so we're coming back to this example. Uh, so we are defining the mapping as phi of x is equal to x mod 6. That is, whatever number given to us, try to read it using mod 6. As simple as that. So you are going to read in between 0 to 5. Fine. Now, try to find what is kernel of phi. That is, kernel of phi is set of all x in z such that x is phi of x is equal to 0, where 0 is in z6. This 0 is in z6 and there is a 0 in z. Please be mindful of both. They are totally different. Okay. Can you guess what will be the kernel of this homomorphism? Can you please leave your answers in the chat? What will be the kernel of this homomorphism? So we will try to verify. We will try to verify what happens here. So phi of 0 is 0. Phi of 1 is 1 mod 6, which is going to be 1. Mahesh, please be careful with your answers because Z is a group with a different operation and Z6 cannot be a subgroup of Z. So we are observing that kernel of phi is a subgroup. Karpanam, yes, good observation. It is nothing but integer multiples of 6. I think Mahesh was referring to 6Z. 6Z, I guess. Okay, fine. Yes, it is 6Z. Let us check what happens. So phi of 1 is 1 and phi of minus 1 is you need to read minus 1 with respect to mod 6. So what happens is it is going to be 5. So minus 1 is congruent to 5 mod 6. try to use that factor. Okay. So phi of 2 is 2 and phi of minus 2 is 4. Phi of 3 is 3 and phi of minus 3 is also 3, etc. If you move on like this, you will get phi of 6 equal to 0 and phi of minus 6 is 0 because 6 is congruent to 0 mod 6 and minus 6 also congruent to 0 mod 6. Again, when we come back to phi of 7, it is going to be 1 and phi of minus 7 is going to be 5. So, if you look at carefully, whenever we have 0 and multiples of 6, it is going to be mapped to 0. Otherwise, it is not mapped to 0. So, kernel of phi is 6z here. Fine. So, in all the 3 examples we did till now, we have seen that it is an observation that the kernel set is a subgroup. So, we will state down the fact and we will prove one more interesting fact. And here you can check one more thing. Phi of 1 is 1. Inverse of 1 is minus 1. So please check where it is mapped to. Can you observe something here? In all these, phi of 1 is 1. With respect to addition, its inverse is minus 1. Please check where it is mapped to. Where these two elements are mapped to. Phi of A, in general, check where phi of A and phi of A inverse are mapped to. If phi of A is mapped to B in the codomain, where phi of A inverse is mapped to? Can you have a guess now from these observations? From this mapping, maybe? Okay, so maybe I will give you a hint. What is the relation between 1 and 5 in Z6? Or what is the relation between 2 and 4 in Z6? Yes, Mahesh, correct. It is nothing but inverse of B. That is, I can write this as phi of A inverse is inverse of phi of A. Pranati, good observation. Yes, it is n minus phi of A because inverse will be n minus x. Fine, good. This is Z6. So in general, if we are trying to write this, it is nothing but phi of A inverse will be inverse of phi of A. Okay. So we will try to list down all the facts and then we will move into the next part. So it will be a quick fact check. Facts. We'll state down all our facts. The first one is the last one which we stated. Phi of A inverse will be phi of A the whole inverse. Kernel phi is a subgroup of G1. 2. 3 is the most crucial one. In fact, kernel phi is a normal subgroup of G. Always, whatever be the mapping, even if the domain is non-abelian, if it is non-abelian, still kernel phi is going to be a normal subgroup of G. Okay, so we will try to quickly prove that and we will wind up for today. Fine. So, if suppose have we proved kernel phi is a normal subgroup, you can define the quotient rule with respect to kernel phi. So we'll quickly try to prove kernel phi is a normal subgroup. So how do we prove H is a normal subgroup? We have stated 3 definitions. I'm going to use the third one. That is, let G belongs to G and N belongs to H, the subgroup. We need to show G and G inverse. Say maybe I will take it as H. G H G inverse belongs to H. That is what we need to prove for kernel phi to be a normal subgroup. Okay. Good. Now here our group is, let G belongs to G1 and let H belongs to kernel phi. Fine. Consider two elements. We need to show G H G inverse belong to kernel phi. So what we know is phi of H is equal to identity. That is what we know because H belongs to kernel phi. Now we need to show G H G inverse belongs to kernel phi. That is, we need to show phi of G H G inverse is equal to E2. Am I correct? Fine. Now we need to show this. Let us check what this is. By homomorphism property, this is nothing but phi of G, phi of H, phi of G inverse. By the first one, I can write this as phi of G the whole inverse. Now use this. We get this to be the identity. So it will be phi of G into phi of G the whole inverse. And these two are elements in G2. So one is the inverse of other. So this will be nothing but E2. So this says that GHG inverse belongs to kernel phi, and hence given any homomorphism between any groups, the group need not have any special property, then the kernel phi is going to be a normal subgroup of G, the domain. So among all the examples which we did till now, you can easily check from the mapping that 6Z is a normal subgroup for the last example. And before that, we checked the singleton 0. Singleton 0 is a normal subgroup. The same way for the first example, we had 0 and 3. So 0 and 3 is a normal subgroup of Z6. So what our aim is going to be is, we are going to say something is a normal subgroup using homomorphisms. That is what our aim is. So in the next class, we will define quotient groups using normal subgroups, and then we will proceed on to the first fundamental theorem. Okay. So I think we can wind up here for today. We will let you know about the classes tomorrow in the Telegram group. On what topic tomorrow's classes will be. We are not yet sure about the classes, on what topic it is going to be. So we will inform about tomorrow's classes in the Telegram group. Stay safe and thank you. Even if you have any clarifications, you can always leave out a message in the Telegram group or in the chat so that we can discuss. I think we will wind up for today. Thank you.